In 2020, Sir Roger Penrose won the Nobel Prize for establishing black holes are real and that at their interior, general relativity predicts a singularity, where space-time trajectories come to an end. This may also lead to a curvature singularity, where measurable quantities become infinite. But recently, another black hole pioneer, Roy Kerr, claimed that Penrose's proof of a singularity had a simple flaw. This was widely reported across the net, with one YouTuber, Sabine Hossenfelder, even going as far as to say,
"This is the maybe most surprising development in theoretical physics I've seen for a decade."
But months after Kerr's preprint paper emerged, it still hasn't been published in a journal. This made us wonder if it wasn't Kerr who was in error rather than Penrose. Sure enough, when we spoke to leading experts in relativity, they confirmed our suspicions. So in this film, we'll hear from Penrose and his colleagues, who will show why Kerr is wrong, and that Einstein's theory of relativity really does lead to its own demise in the extreme curvature conditions inside a black hole and at the Big Bang.
It's a reasonable argument to show that if curvatures get that extreme, then classical space-time is not a good description anymore. And so that you get something which has to have a quantum description, some sort of quantum gravity.
Singularities, curvature singularities cannot exist in reality. So what the theorems are proving is that, as far as we know, and with the theory that we have now, there is a problem.
New physics is thought to be needed to fix this problem. But if Kerr is right, then the need for quantum gravity or some other proposal is undermined. So it's crucial to know if relativity really does predict the incompleteness of space-time, known as a singularity.
Are there singularities in the real world, nature? No. What does general relativity predict? And the statement is that there are ample situations in which general relativity does predict the formation of a singularity.
To understand Kerr's argument, we'll need to learn a few basic concepts. In relativity, space and time are fused into a single entity, space-time. Those that travel through space at high speeds travel through time at low speeds, and vice versa. So to measure space-time intervals, physicists use a geodesic.
Geodesic is essentially the path that an observer would follow in space-time, but just following the curvature of space-time.
The idea is very simple if you are thinking about the curved geometry and traditional things. So a geodesic is the shortest curve on the sphere, for example. So the meridians on the sphere are the shortest curve. So it's not the straight line because you cannot go through the Earth. Okay. Now, if you go to relativity, the thing is that these geodesics sometimes do not measure length, but measure time. And then they make time the longest, not the shortest. Geodesics are the paths when you put in free fall. If, for example, if you are a fan of throwing yourself with a parachute from an airplane, then you will be in a free fall and on a geodesic.
What the Penrose singularity theorem proves is that inside a black hole, geodesics become incomplete.
And what does it mean now for these geodesics, these highways, to be incomplete? It just means they have dead ends. It could be in time or it could be in space. If it's in time, it means the observer who is moving on these free falling in these places could in future their time end, so their clocks stop working.
You could have a space-time that is geodesically incomplete, but which nevertheless does not necessarily have a curvature singularity. That being said, are more common examples of singularities like the singularity at the center of a black hole, or that of a putative Big Bang cosmological singularity. Those would be examples where we have both geodesic incompleteness and an actual curvature singularity, an actual blow-up of the space-time curvature.
This concept of a geodesic is crucial because the Penrose singularity theorem only shows geodesic incompleteness. But in order to say the lines of a geodesic are incomplete, we have to measure their extent through space-time. With this, a complication arises, because in relativity, anything without mass has no passage through time. So we get different types of geodesics. For example, null geodesics for massless particles that move at the speed of light, and time-like geodesics for particles with mass.
You can have particles with mass. They always travel with less than the speed of light. Now, a photon has zero mass, and it always travels with the speed of light. Well, that's light, after all. So a photon is light. So it travels with the speed that its name tells you. So that is a null geodesic.
There are also multiple notions of time. For example, proper time and coordinate time.
Proper time is the time as measured by a massive particle, say. You could say a clock, which has nothing to... I can have a particle moving over here and a clock over there, and if the gravitational field is different there from here and so on, then the clock over there will not measure the time that this particle measures. So that's not proper time. That's the time of that clock. The proper time of this particle is the time it determines itself.
Yeah, proper time is something attached to every particle, or if you want, to every person. You can think about that as your heart, bim, bim, bim. And this is the same for everyone.
Coordinate time, on the other hand, is directly related in black holes to the time measured by a distant observer. And different observers can measure different times depending on their motion. So in relativity, coordinate time has no physical meaning. The singularity theorems claim the lengths of spacetime trajectories are finite. But how do we measure the length of a spacetime trajectory for a photon that has no proper time? We use a measure that is invariant with respect to a choice of coordinates. This is also known as the affine parameter.
So coordinate time would be, one might say that, well, I choose a coordinate which is adapted to my favorite observer. But then you could choose a time which is adapted to your favorite observer and obtain a different answer. And there's no contradiction, but there's no much meaning of just assigning this time using coordinates or using some observer up here. But affine parameter does not need any observer. It is a property of the curve itself. So either the given geodesic has a finite affine parameter or it has infinite parameter. It doesn't depend on any external factors. It is observer independent.
It's this affine parameter that is crucial to what comes next.
Well, an affine parameter applies to geodesics generally. So it might be a time-like curve, it might be a freely moving particle in space-time. Let us imagine that the mass of this particle is reduced until it's almost zero. Well, that means the time along its world line is almost not moving. It's a very slowly ticking clock. When you get to zero, it's a photon. It doesn't even have its first tick.
Now we know the basic terms, we can review Kerr's argument as presented by one of its most eloquent defenders, Sabine Hossenfelder. Keeping in mind there are two problems, one in Kerr's paper and the other in its public presentation.
In the early days of General Relativity, some physicists said that black holes are mathematical artifacts. They can't exist in reality. Then Stephen Hawking and Roger Penrose said, no, it's the other way round. When matter collapses, it's impossible to prevent black holes from forming, and they all must have a singularity inside. These are the famous Hawking-Penrose singularity theorems.
The Penrose-Hawking theorem is about the Big Bang. The Penrose theorem is about black holes. Whilst Hawking was inspired by the Penrose theorem, the two are not the same.
They should have both won a Nobel Prize for it. Unfortunately, Hawking died before that. Penrose got the Nobel Prize in 2020. Kerr now says there's a mistake in that proof. His argument is roughly the following. Hawking and Penrose used an argument about the length of curves. They basically said in a black hole space-time there are curves which have finite length, and the only way this can happen is if there's a point where they end, which is the singularity. The problem is that the length of a curve is usually related to the time that passes on the curve, which is called the proper time. But for light, no time passes. So for the curves on which light moves, you need to measure the length in some other way. You do this by what's called an affine parameter. If you don't know exactly what that is, don't worry. Relevant is just that the affine parameter isn't the same as time, so why worry if it ends? Kerr now says that the Hawking-Penrose proof draws wrong conclusions from this affine parameter. If the affine parameter ends, that doesn't mean that the curves end at any finite time, because those are two different things. In the example he gives, the affine parameter is an exponential function of time. This will be bounded from below, so it kinda ends, but the curve still continues for all times, so no singularity.
That's highly misleading.
This part is highly misleading.
I mean, a null geodesic, if its affine parameter stops, it stops. There is no way of continuing a null geodesic and having its affine parameter stopping and then something starting up. I mean, it doesn't make any sense.
Affine parameters, I mean, the definition of affine parameter works for every geodesic. It doesn't matter whether it is a light-like geodesic, time-like, or space-like. And this is the thing you have to use, because this is the good parameter to measure the extension of the curve. You cannot talk about length, because sometimes it's time, and sometimes for null curves it's something else. So this is the first thing. The second thing is that it's true, the Penrose theorem only proves incompleteness of null geodesics, but the other theorems prove incompleteness of time-like geodesics. For example, Hawking-Penrose and Hawking theorems. And in that case, this is time, proper time that ends. So, but then the third part, which is the most confusing one, and this is where they make the trick, is that she starts comparing affine parameter with proper time. Okay, there is no proper time for null curves, so we will use affine parameter. But then we compare this with time. You see, they forgot about proper time. They just have time. And this is a problem, because if you compare this with a time coordinate, and this is what they do in the paper, then you are comparing something that has no physical meaning with something that has physical meaning.
Ultimately, Kerr finds coordinates where the passage of time is infinite, even though the affine parameter is finite, and so claims to have undermined the singularity theorem. But is this really meaningful?
Having read Roy Kerr's paper, there are many aspects of it I enjoyed, particularly the historical aspects about how he developed his ideas. There are some sort of rather strange polemical remarks, which one can ignore, but having read it, I really found where the bodies are buried in this paper, and he's making a very simple mistake that we typically handle in a very early course on general relativity theory. He's trying to measure a geodesic using a very bad coordinate, and he's giving physical meaning to that coordinate when he shouldn't. So, for example, imagine you're sailing a ship across the globe, and a great way to describe the motion of that ship is to give the latitude and longitude of the ship as a function of time. So the captain records in his log every morning the time of day and the position of the ship. This gives you a very precise description of the trajectory, and in this analogy, the surface of the Earth is exactly the space-time, and the time measured on board the ship is the analog of the affine parameter. So we get a perfect description of that trajectory. Now, you can also choose to use a very bad coordinate to describe exactly the same trajectory. For example, I can imagine as a meter stick. Suppose I measure the distance by using meter sticks in front of the ship. Well, if I use an ordinary meter stick, it'll be just fine. But suppose this meter stick is a weird one and it shrinks. Every day it shrinks a little bit. And as it shrinks and it shrinks and it shrinks, it seems that the ship is going a lot further because it's doing many, many more meters in a day, because the shrinkage of the meter stick is making it look easier for the ship to go a distance. And if the meter stick shrinks to zero size, then it looks like the ship is traveling an infinite number of meter sticks in 2 seconds. So as a result, you see that in a finite period of time measured on the ship, if you're using a shrinking meter stick, you can get an infinite elapsed distance. And that's the mistake Roy Kerr is making. He's using a very good clock on board the ship. He's using the affine parameter on board a particle or an affine parameter on a photon, but he's measuring it against the time measured by an observer at an infinitely far away or at a great distance from the black hole. That time is notoriously poor and gets worse and worse and worse as you approach the horizon. It is exactly like the meter stick shrinking to zero size. The Schwarzschild time coordinate gets dilated to zero when you get to the horizon. It is a disastrously bad coordinate to use at the horizon scale.
Another popular YouTube channel, PBS Spacetime, put the argument this way.
Penrose's theorem shows very convincingly that affine parameters are bounded inside black holes, and so null geodesics end. He then took this to infer the inevitability of singularities as dead ends in the grid of spacetime. But Kerr points out that these affine parameters don't track time in a meaningful way. The affine parameter could be an exponential of coordinate time. This function is bounded from below even though time can go from minus to plus infinity. So that limit of the affine parameter doesn't mean that time itself comes to a halt.
But what do you mean by time? I mean, time isn't a concept in general relativity which makes sense on its own. Time is a local thing which refers to, say, individual particles. Massive particles have their own notion of time. There isn't a time which is supposed not to agree with the affine parameter. I mean, the affine parameter has nothing to do with a clock because it's going on a null ray. It's a null geodesic. You can't have a clock on a null geodesic. It's got to be a massive particle having a time.
And this is the crux of the argument in the paper. And this is just wrong. And the problem is that this is so well known. I mean, this is explained in textbooks, in courses. I explained this in my course in GR. My students know. I mean, if you compare the length of a curve of a geodesic in any of the black holes, and if you compare this with the time coordinate, say outside, the time coordinate will become infinite. But this is just because this is a bad coordinate.
Roy Kerr uses a bad coordinate that gives you the impression that a finite piece of geodesic is actually of infinite extent, and it isn't. The problem is the coordinate you're using to measure that extent. The notion of affine parameter does continue to exist, and we can ask if the affine parameter is finite or is it infinite. And this is a statement which does not need any arbitrary inputs, such as the one that Kerr used to introduce that coordinate. And this is something that, again, many graduate students know that they should not trust conclusions drawn on some random coordinates. Roy Kerr has made this mistake about using a coordinate time. But the problem has got muddied by some of the popularizers because there's a second issue about the role of an affine parameter. And by focusing on the affine parameter, which Roy Kerr thoroughly understands as being a great parameter for describing null geodesics, they have distracted from Roy Kerr's mistake, which is to try and understand the physics of a null geodesic using a completely bad coordinate, the time measured by the observer at a distance, to describe the null geodesic.
Now, if you're trying to say that the affine time is not a good measure of time, because somehow it can stop without the light ray stopping, that's just wrong. You see, if you have a geodesic, an ordinary geodesic, say a freely moving particle, it has a time associated with that mass, determined by the mass of the particle. It has a frequency, a natural frequency, which gives it a time. So that there is a time measure along that time-like geodesic, which is the path in space-time of a massive particle. Now, if we speed that up, make that particle go faster and faster, then that time measure goes down to zero. So once it becomes a photon, then the time measure upon the light ray does become zero. So it's the real time, if you like, is useless. But if you keep the affine time, the affine parameter, then it makes sense because you can scale it up so that as the particle becomes less and less massive, you compensate by scaling up the time accordingly. And then it becomes the affine parameter on the light ray. So it's a perfectly natural idea which applies to a massless particle. Otherwise, the time's just zero, which is no use. You can say zero comes to an end without the light ray coming to it. Yes, it does. So if you use ordinary time, it doesn't do any good to you at all, because it becomes zero when you don't want it to be zero. Whereas the affine parameter remains finite.
Despite these problems, Kerr's work has been praised by physics popularizers.
Paper Kerr doesn't mince words. He writes, "Why do so many believe that the star inside must become singular at this moment? Faith, not science. 60 years without proof, but they believe." It seems to me that Kerr's argument is almost certainly mathematically correct.
No, Kerr is not mathematically correct. No, the affine parameter, there's nothing else you can use for a null geodesic.
And then there's this sentence. I mean, yeah, come on. I mean, we are all idiots. I mean, no, we are not idiots for 60 years, really. I mean,
I've known Roy for a very long time because he was a professor at the University of Austin when I began my graduate studies up there. Of course, he was a famous figure. He was extremely respected. But I think it's also fair to say that Roy has not been so active since he went back to New Zealand. And so some of the things he has said in the recent years is not completely accurate as to what people in general relativity know or what they believe.
Kerr argues, you see there are null geodesics with finite affine parameter. This is correct. But time goes from minus infinity to infinity. Time. This means the time coordinate. And he does this argument also in between horizons, which is even worse because the t coordinate there is not time. So it's completely wrong.
If you read Roy Kerr's paper, it's not hard to actually dig the mistake out. And the next time I teach a course in general relativity theory, I'm going to assign Roy Kerr's paper as a homework problem to find the mistakes.
According to leading relativists, Kerr's argument fails. That doesn't mean singularities are real, but rather we need to look to new physics, perhaps quantum gravity, to resolve what really happens inside a black hole and at the Big Bang.